Okay, welcome back. So this is the second lecture on 10.4, divergence and integral test. Okay, so let's go back to that harmonic series. And it looks like this. So sum n equals 1 to infinity, and the formula is 1 over n. Okay, let's write couple terms. 1 over 2 plus 1 over 3 plus 1 over 4, etc. So yeah, the question is, does it converge? Does it diverge? And if it converges, what is the sum? Okay, so we can see that the terms tend to 0, right? So let's write it down. Terms tend to 0. But that doesn't mean anything, right? Because when terms tend to 0, we don't know whether it converges or diverges. So what I will do, I will graph a function 1 over x, y equals 1 over x, and that function, right, corresponds to this one, right? So so this is the graph of y equals 1 over x. Let's make it green. So now what I will do, I will form a rectangle along this line, along this curve, that correspond to the terms of this harmonic series. So this is y equals 1 over x. Okay, so let's say, how should I do it? Let's say this is 1, 2, 3, 4. It's not, this is supposed to be a square, but it obviously is not. This is 1. Okay, so this is my first rectangle. This would be my second. And here, the next one. Alright, so this is 1, 2, 3, and 4. So you see that the widths of those rectangles is just 1. And now the coordinates of this point is 1, 1. Here I have 1 over 2, 3, 1 over 3. Alright, so now the areas of those rectangles, right? So this, right? So the height of this one is 1, and the width is also 1, even though, right, it doesn't look like a square. It's supposed to be a square. It kind of depends on what you assume one unit is on the y-axis, right? Anyway, so I'm looking at the areas of those rectangles, and there's sum. And the question I'll be asking is, well, does the sum of those areas equal to a certain number, or it just goes to infinity, right? So that's, we can draw this one as well. Anyway, so here is the sum of the areas. So that's going to be that, right? 1 plus half plus 1/3 plus 1/4, etc. Okay, so you can see that the areas of this of those rectangles, right, correspond to the terms of our sequence. Okay, so 1 plus 1 over 2 plus 1 over 3 plus etc. Okay, so now we can use calculus, right? We can we can maybe figure out the area under this curve, right? And then say, well, since the area of the rectangles, and we can figure out whether the area of that under this curve converge or diverge, right? So we're gonna, so the area of under the curve, and 1 over x, right? And we'll find that area from 1 to infinity, right? So you see that's gonna be improper integral. And it will look like this. So I use my integral from 1 to infinity, and I have 1 over x dx. Right, so what I did, I simply took the function that corresponds to the formula for my series, and I'm taking an improper integral of that function. And we know how to do it, right? So we convert it to limit with b approaching infinity, and then the limits are 1 to b of 1 over x dx. Okay, so antiderivative of 1 over x is natural log of x. Everything's positive. We don't need absolute value. My camera just moved. Let me refocus it. Okay. So b approaches infinity, and I have that, right, antiderivative of 1 over x, natural log of x, and the limits of integration are from 1 to b. Okay, so I have b approaches infinity, natural log of b minus 1, minus, not 1, natural log of 1. Okay, so now, well, this natural log of 1 is just 0, and here, since b approaches infinity, well, natural log of b also approaches infinity. So the limit doesn't exist, so we can conclude the integral diverges. Or also we can conclude that the area is infinite. And since right, the area of the region under the curve is smaller than the area of those rectangles, right? We can also conclude that this series, or the sum of those, well, the series or the sum of those terms also diverges. Okay, so let's write it down. Area of rectangles is greater than the area under the curve. Okay, let's write it in symbols. So from n equal to 1, infinity 1 over n. So that, right, that the sum of the series is greater, or the area of those rectangles, right, represented by, or rectangles represent the terms of this series, is greater than the area under that curve. Okay, so here's our conclusion. Harmonic series diverges. Okay, so the integral test is based on this argument. Okay, so let me write it down. So now we have some conditions for that function, right, that corresponds to our series. So if function f is positive, right, so above the x-axis, continuous and decreasing, for all x's greater or equal than 1, and right, that series formula matches with that function f. Yeah. So that means the series matches, corresponds with function values. Then we have this relationship, right? So the sum with n equal to 1 to infinity a sub n, and that improper integral from 1 to infinity f of x dx. So now they either both converge or diverge. Or both diverge. Okay, so this is kind of, I don't know, I hope this is clear. I'll give you a bunch of examples. And hopefully that will clarify things a bit. Okay. Okay, do I need to look at that? Let me review what we just did with those rectangles, right? So let's go back to that example again. Alright. So we had, so here's our formula. Right, here's the corresponding function. So f of n would be 1 over n. Now let's check it, right, against our conditions. So the function is, well, if n is greater or equal than 1, well, then the function is positive. Well, definitely continuous. And decreasing. Right, so we saw the graph a minute ago. So I have that sum from 1 to infinity of a sub n. Now let's just write 1 over n, and I have that improper integral, right, from 1 to infinity 1 over x dx. So that's my improper integral. So using this theorem, right, so since the integral diverges, we conclude that the series diverges too. Okay. All right, examples. So this is some general example that we have already seen, right, a minute ago. Let's look at something we have not seen. So example, I think it's 8. So the series looks like this, so from 1 to infinity, and then I have 1 over n squared plus 1. Okay, so let's write a couple terms. The first one will be 1 over 2. The second one will be 1 over 5. And then for n equal to 3 will be 1 over 9. 1 over 10. So 3 squared plus 1, 10. Then the next one will be 16 plus 1, 1 over 17. Okay, so it keeps going. So the terms tend to 0. Right? So it could be either way, diverges or converges. So we need to use this test, right? So that's the tool that we have. Let's use it. So let's write that corresponding function. We can use n or x, it doesn't matter. So f of x is 1 over x squared plus 1. So next thing we do, we check it against our conditions, right? So it would be a good idea to graph it, right? To see whether the function is decreasing, right? Especially this part maybe sometimes is not satisfied. So the function is positive, right? For x is greater or equal than 1, well, for any x, right? In fact, then the function is continuous. Again, you can look at the graph, and the function is decreasing. So all those conditions are satisfied. So positive, check, continuous, check, and decreasing. Okay, so that means we can use our integral test. So here we go, right? So I formed that improper integral, so from 1 to infinity of that function, 1 over x squared plus 1 dx, and then we have that limit with b approaching infinity, 1 to b, our limits of integration. Here's my function, 1 over x squared plus 1. And I hope you guys recognize what that is, right? What this is, the antiderivative of that. Well, it is the inverse of tangent, right? I don't need this anymore, I need this. B going to infinity, and I have my arctangent, and limits of integration are 1 and b. So 1, let's put the vertical line on b. Okay, so let's plug them in. B is tending to infinity, and here I have arctangent of b minus arctangent of 1. Okay, so if b is going towards infinity, this whole thing tends to pi over 2. Okay, and now the inverse of tangent of 1 is just pi over 4, 45 degrees, right? So this is pi over 4. Alright, so we get, what do we get? we get pi over 2 minus pi over 4. So that's pi over 4. Alright. So now what? Now we know that that integral, improper integral, converges. Okay, so we have that pi over 4. So the function has a limit, right? Or that improper integral has a limit. So that the conclusion is the integral converges. And then, based on the theorem, we can say that the series converges. Well, unfortunately, we don't know what it converges to, right? Because the fact that integral converges to pi over 4 doesn't mean that the series converges to pi over 4. Okay, that means let's wrap it up. So let me just write a warning. So integral converges to some number. Oh, let's just use that pi over 4. Okay, some concrete, specific number. That doesn't mean, alright, we cannot conclude that the series converges to pi over 4. Okay, so let's stop here.